Hi everyone, and welcome to our second video cast of the Biopsych unit. Today we're going to be focusing on the building blocks of your neural system. So remember, yesterday we talked about the nervous system and the endocrine system, and I mentioned different types of neurons and neurotransmitters, and then of course hormones in the endocrine system. But today we're really going to focus on what are those neurons made up of, and how do they talk to each other, and what does that process look like? So, a couple of things, right? A neuron is the basic block, like the building block of your nervous system. So it's made up of billions and billions of neurons, right? And it's a cell that communicates, and it communicates through electricity and through chemicals, okay? So we already talked about these different types of neurons. I mentioned them in the previous VODCAST. So you have sensory neurons, which carry in information from your senses. They're afferent, remember, same, sensory, afferent. Then you have motor neurons, which go from your spinal cord out to your muscles and organs. So those are motor afferent, right? So they allow you to move. And then you have interneurons that are in your spinal cord and in your brain, and those send the messages between the motory and the sensory, okay? One more type of neuron I want to introduce to you today is called the glial cell, okay? It's right over here, all right? And the glial cell provides structure and support for the actual neuron. So basically what it does is it creates the myelin sheath, which I'll talk about in a little bit, removes waste, those kinds of things, okay? The myelin sheath is this little yellow thing here that looks like, I guess, little hot dogs all strung together, and it actually protects the neuron. Okay, so let's talk about the basic parts of the neuron, okay? First things first is the cell body. So all cells have a cell body, right? They have a nucleus, okay? And this is the cell body right here, okay? Cell body, nucleus, okay? Now, attached to the cell body are these things called dendrites, right? They look like little fingers, okay? You see these little like branch tree-like things here, okay? And these detect messages. So dendrite detect, right? So they like hang out there and then they start to hear a message and they're like, they listen, right? Okay, and then they detect the message, okay? They detect the message, move the message into the cell body, right? And then from the cell body, it goes into the axon. And the axon actually sends the message away from the cell body down to towards the next set of dendrites, okay? If you think of it, axons send messages, axons away. So dendrites detect and axons send away, okay? Or axons away. So they send the message away from the cell body. And then, like I said, you have the myelin sheath, right? This myelin sheath is this blue stuff over here. It kind of looks like it's all wrapped, okay? And this is literally a fatty tissue that is like wrapped around the axon, and it allows the axon to speak like quickly, okay? And each myelin sheath has a little separation in between them, and these are called the rods of Ravinier, and these are basically little spaces in between the myelin sheath, okay? This myelin sheath is very important for messages to be able to send quickly. If your myelin sheath erodes, you start to have different neurological disorders, okay? So, we have people who have Parkinson's, and the name is escaping me, of course, but where they shake, right? And the reason a lot of times, multiple sclerosis, thank you. A lot of times the reason is, that's the tip of the tongue, right? Is that their myelin sheath is deteriorating, and so the messages don't send as fast, and so they're not able to the brain is not able to communicate with the body very well. Okay, so we know the basic parts of the neuron now, right? So certain things go on inside of the neuron when it's sending a message, okay? The first thing is that when a neuron is not sending a message at all, it's in a state called the resting state. It's resting. It's chilling out, waiting for a message, okay? It's preparing to be activated. In this resting state, there are potassium and sodium ions that are inside and outside the neuron, okay? For the most part, you have potassium ions inside and sodium ions outside, okay? And a couple of them go back and forth, right? But for the most part, you have a negative charge inside the neuron because there's more potassium positive charges or more sodium ions outside the neuron, okay? So if you think of a neuron kind of like a battery, you would plug a battery in to start it up, okay? So this is like the battery is just chilling, it's not plugged in, okay? It's just kind of at a resting state, and it's actually a negative charge. So currently, when there's nothing going on in your neurons, they're charged negatively, okay? So what happens is in order for the neuron to become active, it's like a battery, you have to plug it in, okay? The plugging it in is called the action potential, okay? This is like an electrical impulse, a flash of lightning it's electrical charge that travels down the axon. And as it travels down the axon, certain specific things happen with the potassium and the sodium ions that allow the axon and the neuron to send the charge, okay? So what happens is something called depolarization. Depolarization is when the axon has these gates that open up, and those potassium ion, or those sodium ions, excuse me, right, Na, they flow inside. Okay, they kind of flood the axon. They flow inside very quickly, while some of the potassium ions leave, right? But they flow out a little more slowly. And this actually causes the neuron and the axon to become positively charged. So when the sodium ions flood in, right, because of the action potential, it becomes depolarized and it has a positive charge, okay? Now, after it becomes depolarized, positive charge, the message is sent, right? The positive charge kind of jumps from one node of Reuptake to the next. So remember I said that this is the little space in between the myelin sheath? So this is where the action potential actually happens. It happens here, and then it jumps to the next one. It happens here, next one happens here. And when that's happening, right, this message, this action potential is being sent down the axon, okay? So after this red, where you see the red that sends the message here, and then all of a sudden you see the next picture, it moves to the next node of Reuptake, right? So what happens is you have to replenish, okay? What happens is a refractory period. The neuron pumps back out all the sodium ions, right, so that it can be a stable environment again. And it actually does it in such a way that for a moment, there's actually too many potassium and sodium ions outside, and so nothing can happen. It's called the refractory period because no messages can be sent at all, right? So before it totally replenishes, it has this refractory period where the sodium ions are going out, but some of the potassium ions haven't come back in, and so it's at this point where it can't fire and it's just completely done, and then it goes back to its normal state. So this maybe makes a little bit more sense if you look. So this is the resting potential right here, okay, you see here, and then you see this threshold. This is like you plugging in the battery, right? And then the sodium ions come in, and it goes up, and then it starts to go down, and the sodium ions go back out. But this moment right here, do you see it goes below the resting potential where it should be? That's because for that brief moment, and it's like not even a millisecond, there's too many potassium and sodium ions outside of the neuron. And so for a moment, it can't do anything, and then it goes back up to resting, okay? A couple of things. This threshold has to happen because basically it has to be a minimum trigger. If you think about it, you can't plug in a battery or electrical circuit halfway. You have to plug it in or not at all. So your neurons are the same way. They either send or they don't. They don't halfway send, okay? And the way that they send is they get different messages. So they get excitatory and inhibitory. Excitatory is like, yay, send, green light. Inhibitory is like, stop, red light. And so what happens is if it gets enough, yay, send, then it'll go, okay? Here's the deal, all or none. Like I said, the neuron has to be completely stimulated or not at all. And the direction only goes one way at a time. So it can carry a message back and forth, but at a time, it only goes one way or the other, they don't crisscross. Okay, so if I want to talk I want two neurons to talk to each other, okay? Because obviously the message has to jump from neuron to neuron. So what happens is the action potential, like we just talked about, right? That's the sodium and the potassium in and out. This actually reaches the axon terminal. So it goes down all of those little nodes of Reuptake. You see all these little spaces here, right? Jumps, jumps, jumps. And then it reaches the end. And this is called the axon terminal right here, okay? And when it reaches it, these are it has inside of it these little synaptic vesicles. And these synaptic vesicles look like little marbles. And inside of the synaptic vesicles are actually neurotransmitters. And neurotransmitters are the chemicals that have the message inside of them. So while you need the electric current to send the message, you need the chemical to actually tell you what the message is. The neurotransmitter is a chemical that actually tells you what the message is. Is the message to talk? Is the message to write? Is the message to think? Is the message to sing? Is it to laugh? What's the message, okay? So the axon terminal, right, they have these little terminals, buttons at the end, okay? And they have these little synaptic vesicles, which are those little pouches that look like marbles, and inside of them are neurotransmitters, okay? So what happens is that the neurotransmitters jump, they go like this, bloop, 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 right? They jump right here. You see this right here? Okay, across this big black hole called the synaptic gap. And they jump, bloop, 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 and they attach to a new neuron, right? So they jump from the synaptic vesicles, right? They jump from the axon terminals to new dendrites, right? They have new receptor sites on the dendrites, okay? And the dendrites then listen, and then they send a new message, okay? So the synaptic gap is just the space in between the axon of neuron 1 and the dendrite of neuron 2. So you see here, this is that little space right here where my cursor is, okay? It's very, 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 very tiny. You can't even really see it with the naked eye. We used to think that there was no space at all and they were connected, okay? So synaptic gap. Okay, once the neurotransmitters have connected like they do down here, right, they jump bloop, 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 bloop across the synapse, then they get sucked back up into the original neuron they were in by a process called reuptake. So reuptake, literally like a vacuum, right? They get sucked back up like a vacuum into the presynaptic neuron, okay? And so if you think of it like, So the presynaptic neuron, okay? So what happens is it's literally like a vacuum, and they send bloop, 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 and they go send bloop, 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 right? It sucks them back up, okay? So that's reuptake. Okay, so I just wanted to show you this kind of like a breakdown, maybe in a little more depth. So if you see here, we have, this is the cell body, right? And this is the axon, and this is the action potential, right? And the action potential, sodium and potassium ions, it travels all the way down. Then it gets to the end, right? And this is the end, okay? It's the axon terminal, and they have the synaptic vesicles inside, right? And the synaptic vesicles, bloop, 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 right? They jump into these, the neurotransmitters, they open up. So do you see how this is the vesicle, it's inside, and then it goes to the edge here and it opens up, and they bloop, 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 and then they reconnect to these little receptor sites that are on the dendrites of the next neuron, okay? So it's closer up. Here's another picture, okay? So you see you have the presynaptic and the postsynaptic. So this is the neuron that's sending, and this is the neuron that's receiving, okay? So the action potential goes down the axon. Here's the vesicles. They fall to the end. Then all of a sudden the neurotransmitters, bloop, 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 they attach, right? And then they get sucked back up. And here's the deal, right? All neurotransmitters are like locks and keys. So the neurotransmitter has a special shape and the receptor has a special shape, and they have to match up. Otherwise, they can't send. So if you look here, like this neurotransmitter can't send in this receptor, but that one can, okay? So we're going to talk about neurotransmitters in the next video and more detail on what each neurotransmitter does. But that's all for now, AP Psychos. And remember, psychology is flippin' awesome.